embarrassing. Okay, hello YouTube, we're live. Can we do that? Low latency. That's fine. It doesn't matter. Okay. Alright, we're gonna have... I'll put this on. Okay, hello everyone. Welcome to TypeScript London. Thank you so much for coming. My name's Alistair. I have to the left of me Simon, who's going to do the very first talk, which is very important. Could be life-changing. It's a fire talk. You know, you'll all see. Cool. Thank you very much.
Exactly. Hello, everybody. Hi. So my name is Simon Wegmans. I work at Vercel, the little triangle company here. I used to work at Cloudflare, who have been incredibly amazing by giving us this room today. So I want to tell you a little bit of a London story. About 3 months ago, Vercel did a Next.js meetup at which we invited a bunch of power users of Next.js, of which the wonderful people of Hop.io and Alistair showed up. During that event, loosely he mentioned, hey, I might actually want to do a TypeScript event in London, meet the community, that kind of thing. And well, that's kind of how I am. I started then really thinking about it. I'm like, that could be really cool. And I started chasing Alistair like, we got to do this. People want this. We should do it. And here we are today. I can't begin to express how amazing it is that everybody made it here. And actually, Alistair last week asked me to do the opening session, which is amazing. The safety session. So, emergency exit on the left and on the right. There's fire marshals at the front desk. Please listen to them in case of a fire. If it goes a little bit wild in here and alarms go off, direct yourself to them. There are drinks, there are snacks. The bathrooms are on the right over there. And that's pretty much that. Quick shout out to our sponsors and supporters. So I already mentioned one of them, Hop.io, another one, Cloudflare, but also Vercel, and you'll see after why. And also the amazing person here, Scott, who's live streaming this. So a quick reminder, this is being live streamed, although the camera is directed at the speakers. If you do not want to be streamed live, just not go in this area. So there we go. Without further ado, I would like to ask Brandon to the stage.
Hooray! Amazing. Let's see, can I... Sorry about this. There we go. Right. Great, can you all hear me? Is this good? Amazing. Okay, so hello everyone. Welcome to my talk on how we automatically generate TypeScript definitions for the Cloudflare Workers runtime using TypeScript. So a quick introduction. I'm Brendan. I created Miniflare, which is a fully local simulator for Cloudflare Workers. And I'm now a systems engineer at Cloudflare, specifically focusing on workers dev tooling. So I've mentioned Cloudflare Workers a few times already, but what exactly are they? So can I just get a quick show of hands of who's heard of them before? Cool. And keep them up if you've deployed one before. Awesome. Okay, so Workers are basically like a functions as a service platform. So you write some HTTP handling code, you publish it to our platform, then we give you a URL you can hit to run it. Our runtime provides standard APIs, similar to what you'd find in a web browser, for request response handling. We deploy your code to all Cloudflare edge locations, so your users get low latency access wherever they are. Importantly, there's practically no cold start time because our runtime is based on V8 isolates and not containers or virtual machines. If you're interested in how we do this, there's a great talk from the architect of Cloudflare Workers, Kenton, called Fine-Grained Sandboxing with V8 Isolates. It should be the first results, should be one of the first results if you Google this. So I definitely encourage you to watch it. It's very interesting. In addition to standard web APIs, we also provide some non-standard runtime APIs for things like accessing key value storage. So in this example, storage, the capital storage, is a binding to a worker's KV namespace. And with this, you can get, put, delete, and list values as you'd expect with like a regular key value store. There's also APIs for rewriting HTML responses. So in the previous example, the worker acted as the origin. So when you fetch the worker it would produce the response for you. In this example, what we're doing is the worker is sitting in front of your origin. So we are intercepting responses and rewriting insecure HTTP links to HTTPS ones. So that's just an example of what Cloudflare Workers could do for you. They can sort of be much larger than this, much smaller than this, anything in between. So the key points are we've got this custom V8-based runtime, which is kind of like Node or Dino. We're implementing mostly web standard APIs like browsers, so think like fetch, request, response, web crypto, all of that stuff. But we also implement some non-standard APIs, specifically for server-side use cases, like connecting to Cloudflare databases or HTML rewriting. So with all this in mind, why do we actually want TypeScript types? We obviously want type checking to prevent errors at runtime. We want auto-completion in IDEs, so people can explore the type service that we provide. And for me at least, implementing Miniflare, they're really useful when you implement a local simulator, because you know what the interface for these APIs is supposed to be. So with that quick introduction out the way, let me give you a summary of what we're going to be talking about today, after I've had a quick drink of water. So to start with, we'll cover how we used to do handwritten types a couple of years ago. Then we'll look at our first attempt of auto-generation using C++ AST parsing and Python. Next, we'll see how we do auto-generation nowadays with runtime type information and TypeScript compiler API. After that, we'll look at some transformations we do on these to improve our types. And then we'll focus on manual type overrides to improve the developer ergonomics. And finally, we'll have a quick look at compatibility dates and other future ideas we've got for workers types. So first off, how we did types a couple of years ago. Like most runtimes, so like Node and Bun, we had an npm package providing global types for our runtime. So this is like types Node or Bun types, but for workers. Importantly, this package only included Cloudflare-specific APIs like the HTML rewriter and not web standards. So users would need to include both libwebworker and npm package and this npm package in their TS configs. The problem with our package is that it was handwritten, right? So they were very error-prone to update, and these types weren't typically updated by the team implementing the runtime themselves. So that meant they were slow to update, and on the right, we've got an example of a type error, but this is using a new API that should work on workers, but doesn't because like the types haven't been updated yet. So we've got an incorrect type error here. The biggest problems, though, were with our reliance on libwebworker. So this included APIs like message channel that we didn't implement at all, meaning code that type checked wouldn't actually run in our runtime, and our workers runtime APIs weren't fully spec compliant at the time either. So we hadn't implemented things like the readable stream constructor, but again, this would type check fine because most browsers implemented it. They were also missing experimentalized that we had implemented, like the sort of bring your own buffer stream readers and scheduler, but because these weren't adopted by major browsers yet, they weren't in libwebworker, and then they weren't in our types, which is not great. So now that you've seen all these problems, what should we do about them? So this is a simplified snippet of our C++ code from the workers runtime, specifically the blob implementation. So it'd be great if we could generate the TypeScript types from this, because all of the types are there. And as an aside, we recently open sourced all of this stuff into the Cloudflare Worker GitHub repository, so check it out. It's really cool. For auto-generation, what we need is we need some way of extracting the type information from this runtime code, transforming it a little bit, and then rendering that to TypeScript. So our first attempt, we used these Python bindings to Clang, which is the C++ compiler. We parsed these C++ files into an abstract syntax tree, or an AST, and we extracted the type information from that. In this small snippet of Python code, what we're doing is we're loading a C++ header file into a translation unit, and then we're recursively traversing it and logging it to the console. If we run this program, we end up with something that looks a bit like this, in like text form. And we can see that it's possible to extract methods and types from this tree. What we did is we converted this tree into some sort of intermediate representation. We did some transformations on it, and then we rendered it to TypeScript. And then we had this GitHub bot that made a pull request to our workers types repository every week with the new types so that people could see what was new and always use the latest ones. This worked pretty well, but there were some problems. So the biggest issue with an AST parsing approach is that it's brittle. If you've ever done any work with like ASTs before, you'll know this, that if code structure changes, this is very likely to break. But we won't get easy to debug errors with it, which is a bit of a problem, because it kind of broke quite a lot. Secondly, the headers for each runtime API were parsed in their own Clang translation unit. meaning that each header has its own dependency graph, which is very inefficient because we're parsing dependencies more than once. So it was really slow to run this code. We kind of sped it up by multiprocessing. So we like parsed each header in parallel, but that just added loads of additional complexity, and it was not great. Because we were parsing headers in different translation units as well, we had mismatched like internal type names. So like some types had namespace identifiers, some didn't, and we had some like flaky string manipulation to normalize them. It was not a good time. And all the transformations we made on these types were untyped, and we had like very few assertions on our assumptions, which made it really easy to make mistakes. And we generated TypeScript by like concatenating strings together, just like form TypeScript, which again is untyped and easy to make mistakes with. So this was not a great approach. So we learned from all of this, and we decided to rebuild our auto-generation system from the ground up. So instead of using AST parsing, we used our new runtime type information system, which allows us to query types at runtime. And this system was initially used for automated fuzz testing. This requires us to build the runtime to generate our types, which is pretty slow because we depend on V8, but it's much less brittle, so it's totally worth it. This runtime type information is encoded in a format called CapMProto, which is we use as a language and platform independent binary format, kind of like protocol buffers if you've used them before. It's basically just like a typed version of JSON for all intents and purposes. This is what our CapMProto schema looks like for type information. You can see it kind of maps to TypeScript types. So like bool is boolean, number is number, arrays are arrays, dicts are records, and one-ofs are unions. And we can compose these types into larger structures like interfaces and classes that contain methods and properties. The really nice thing about CapMProto is that you can generate encoding and decoding code from your schema for many different languages. So we can automatically generate like the C++ code and the TypeScript code required to build this binary format. Importantly, this means that we don't have to implement all of the stages of our auto-generation pipeline in the same language. We can encode all runtime API types in C++, and then we can do all further processing in TypeScript, which allows us to use the TypeScript compiler API for actually rendering the TypeScript. But before we get to that, let's have a look at some quick TypeScript internals. So like we had Clang generate a C++ abstract syntax tree earlier, the TypeScript compiler generates those too. There's a great website called astexplorer.net for visualizing these. And if I have a quick demo of this, I hope you can see that. Can you see that? No, you cannot. I'm going to have to do something sneaky. Oh no, that's over there now. Oh dear. How do I get there? This is not going to work. Okay, never mind. I wanted to show you some TypeScript abstract syntax trees, but we don't need to see them. They're kind of like the C++ ones, just slightly different names. All good. Okay, you see the slides again. Excellent. So basically, I was going to show you some abstract syntax trees for KV namespaces. What we want to do instead is, rather than getting the TypeScript compiler to parse TypeScript code into an abstract syntax tree, we want to build the abstract syntax tree ourselves in TypeScript and then print it out. So we want to go the opposite direction. So as an example, we'll try build this KV namespace type. So first of all, we have to build this tree from the bottom up. So we'll start with the key parameter. We'll use that to build a get method, which takes this key parameter and returns a promise to a string or nothing if the key wasn't found. And then we'll use this method in an interface for KV namespaces. And then we will create a placeholder source file and printer, and we'll print out the interface to a string, and then we'll log that to the console. And all of that is just for 3 lines of TypeScript. This is a really verbose API, but with a bit more work to convert CapMProto types into TypeScript, we kind of have auto-generated types. Hooray! Those sitting near the front of the screen will notice that we don't actually have parameter names here. Unfortunately, the C++ compiler kind of strips those during compilation, so we can't access them in runtime. Instead, what we do is something very similar to the first approach and extract those from the C++ AST and then add them in afterwards, which is kind of fine because we're not interested in the types, just the names, and we can do everything in a single translation unit, and it's quite fast. And this pretty much solves all our problems from earlier. So we have new workers APIs included straight away. Unimplemented web APIs aren't included because we're not relying on libwebworker anymore. It matches our partial spec implementations because if the constructor doesn't exist, we don't generate the types for it. And experimental web APIs are included, with all of our minor spec differences and all of that stuff. We still got some problems though. Without any transformations, the iterated values are untyped. We can't find any like global types, so we don't have any global functions or constants, and we don't have any function overloads, so TypeScript can't narrow the return types given arguments. So we need to do something about this. Luckily, all the information we need to fix these problems is already in the types. What we need to do is transform them into a form that TypeScript recognizes. So we'll start with fixing iterators. This is what our types look like at the moment, but we want to really use TypeScript's built-in iterable iterator type instead, because we can just get rid of all of this code. So what we can do is move the string basically to the iterable iterator and inline that type. Side note, keynotes, magic move transitions are so cool. We've got another one on the next slide. To fix globals, we need to do something similar. We need to extract the server worker global scope's members into the global scope. Importantly, we also need to include superclasses here as well. So things from event target, like the add event listener, remove event listener, all that, we want that global as well. So here we go. So how do we actually do this, right? Not the transition. The transitions are actually really easy. You just like enable the transition and it just figures it out. It's so cool. Let's look at a simpler example. So say we want to replace all of the strings in our KV namespace with numbers. I don't know why you'd want to do this, but we want to do this. We can write a TypeScript transformer for this. So this recursively visits all nodes in the abstract syntax tree, and if we find a string token, we replace it with a number. Otherwise, we just keep visiting children. We can use the TS transform API to apply this to an AST node, and then get the result out of that, and print it or do whatever. Use it in something else. Who cares? Let's see what TypeScript is doing when we call this function. So this is the abstract syntax tree I was going to try to show you earlier, but I couldn't. So we'll start at the root KV namespace interface declaration, and then we'll do a depth first search until we find a string, and when we do, we'll replace that with a number and keep going until we found no more nodes. So we'll just keep going, keep going, keep going, keep going, keep going. And when we find a string, we replace it with a number, and we keep doing the depth first search until we replaced all of the strings with numbers. Hooray! So this solves two of our problems. We can apply this technique to our other transformations, and that fixes these. So iterators are now typed correctly, and we can use global functions and constants. Great. But we still have this other problem of no overloads. So how are we going to fix that? For overloads, we need something a little bit more complicated. What we want in our TypeScript types is something like this, where we have a correspondence between the input and output types. So for example, when we specify text, we expect a string, and when we specify array buffer, we expect an array buffer, and so on. The problem is that in our C++ code for KV namespaces, there's no correspondence between these input and output types. So how do we know what to generate? We need some additional human input here. And there are actually a few other places where we need human input too, to improve the developer ergonomics. As we've already seen, we need this for function overloads, where the correspondence between input and output types is not clear. We also need additional inputs to make types generic by adding type parameters. So for example, with readable stream, like the type of items in the stream that are emitted by the stream. Sometimes we might want to rename types to be less verbose. Sometimes we might want to completely replace the auto-generated definition with something else. We do this when we want to use custom construct signatures. And sometimes we just want to hide a type because it shouldn't be exposed to end users. So we solve this by allowing partial TypeScript code to be inserted alongside the C++ code. So you'll see we've got all of the overloads in the C++. And we encode this with the runtime type information in the Kaplan proto. And we can use this mechanism for all of the cases that we just highlighted. Importantly, because we're co-locating the overrides with the C++ code, it's much easier for the runtime developers to add these in and keep them up to date. So you'll see that we've got some like partial TypeScript here, but how do we kind of interpret that? There's a slightly complicated-ish algorithm for this. First, if the override type starts with a TypeScript keyword, we just replace the generated type with that override. If the override is a type alias to never, we delete the definition completely. Otherwise, we use some heuristics to convert the override into a valid TypeScript class by prepending and appending the required tokens to form correct code. We can then use the TypeScript compiler API to parse this added, like this mutated class into a TypeScript syntax tree. And then with that parsed TypeScript class, we can now transform our definitions. So if the override class has a different name, we rename our generated type and any references as well to the generated type to match the new one. We copy over type parameters and heritage clauses. So these are like extends and implements. And finally, we merge properties and methods by copying over new members and replacing existing methods. And I know this was a pretty quick run through of this transform. If you're interested in more detail on how this works, have a look at the worker repo or speak to me at the end. I'll stick a link at the end as well. With that, we've kind of solved all our problems. Hooray! And we have a solid set of type definitions for workers. But there's one more thing we could do to make them even better. Sometimes people make mistakes. Developers are no different, and sometimes they introduce bugs into code. But we don't want, sometimes fixing these bugs would introduce breaking behavior changes. But we don't want to break existing deployed code with these changes that we'd have to make to fix the bugs. So when you upload your worker code, you have to specify a compatibility date too. And we put breaking changes behind compatibility flags, which have a date that they are enabled by default. So if your worker's compatibility date is after a compatibility flag's default on date, that flag gets enabled. So we also allow you to manually enable or disable specific flags. And this means that when you upload code, you know it's going to work forever, unless like something catastrophic happens. The problem is that some of these flags change the public API service and therefore the TypeScript types. So for instance, there's this flag called global navigator, which adds a new navigator constant to the global scope. And the types would be different, right? Because there's this new navigator global type where you have this flag enabled, and if you don't have this flag enabled, you don't get the type. So there are 22 compatibility flags, although not all of them change the type surface. And if we generated a version for each combination of flags, we'd end up with quite a few types. Does anyone know what that number is? It's over 4 million, which is kind of infeasible. We could maybe do it, but we probably shouldn't. So instead, our solution at the moment is to generate an entry point of the types for each compatibility date that changes the public API surface. So we don't generate them for all of the combination of flags, we just generate them for some of the dates that change the API surface. This doesn't completely solve the problem, because users can kind of selectively enable and disable flags. So they could be selecting a date, but with like some flags disabled, which presents a problem, right? Because we kind of just need to have all of these combinations available, but we don't want to. So an option we're kind of considering is like TypeScript types as a service, which would be like a web service that dynamically generates npm packages containing TypeScript definition files based on the compatibility date and flags you've selected, which I think would just be really cool. I haven't seen this done before. I just want to build it just cause. Maybe it's not a good idea, but who cares? Other things we'd like to explore, automatically generating API documentation from types, automatically diffing our types with web standards, so we know when we need to include our spec compatibility, generating bindings for other WebAssembly targeting languages that we support, so like Rust bindings, or I don't know, maybe Go bindings or something. Finally, we'd like to generate these like golden files that we commit to our repo and like have to be updated if you make changes to the APIs, so that we know when we've made accidental changes to our public API service and can kind of prevent that. And with that, we're done. We've covered the history of handwritten workers types using the C++ AST parsing approach to generate types automatically, our new solution using runtime type information and the TypeScript compiler API, transformations for iterators, the global scope and overrides, and finally, how we handle compatibility dates and ideas for future improvements. Types as a service for the win. And that is it. I'd encourage you to try out Cloudflare Workers if you haven't already. You can find all of the type generation scripts in the Cloudflare Worker D GitHub repo. Find me on GitHub and Twitter. And thank you all for listening. I guess I take questions now. Do I? Yes.
Looked like you did the dynamic type generation thing. Would it be at the first install, like those things don't exist at the point when you first do it. It's like the first image sort of super slow, what's in the background is thinking
Yeah.
spun up.
Yeah, exactly. Oh, of course, yeah. So the question was that what would it look like if we did this dynamic type information or this dynamic type generation on the first install? So obviously, yeah, there would be some slowdown on the first time you ran it. We would cache it, that combination of date and flags going forward. I think there would be there'll be some common combinations of flags, and obviously most people probably aren't going to be selecting flags. So for the most part, I think it would be pretty fast. We would only need to do it. We would be able to cache it for each runtime version as well. So we wouldn't need to. We'd be able to reuse some of the dates as well. So there could be quite good cache hit ratio there, I think.
Thank you very much. For the blocks, did you consider the TypeScript configuration file that can, for example, if you want to use some flag, you can import the module with the DJS definition that will extend the API this feature for this block, so
Yep.
it will automatically enhance the extension.
Yep. We did consider that. The problem is that some of these flags interact. So we have a flag that changes how properties are added to types. So they're either added on the prototype or the instance. So sometimes they should be getters and sometimes they should be field properties. And then we have flags that add new properties. So some of these flags, because these flags interact, we'd have to generate combinations of these flags, which is a bit of a problem, and why we kind of want to lean towards this approach.
Did that answer the question?
Yeah.
Awesome. Any other questions? Cool. All right.
Fantastic.
Well,
Thank you very much. Thank you.
Next person is John. Oh, there we go. Just gotta quickly switch the laptop.
Sure.
And we're gonna get some water as well. Should I try to keep the audience warm, or maybe we can do one of those like Mexican waves, or no? We all can like huddle about the previous session, how amazing Cloudflare is. There are quite some cool Cloudflare people here today, though, so if you can mingle laughter about Cloudflare, that'd be awesome. This is John.
Hello. Are we Run my hands. PlayStation browser. Is that thing up there? I can't see. I can see stuff. Yeah, I'm just gonna hit the thing. Cool. Yes. Hopefully. Damn it! I don't mean to see that. How do I stop that?
Do you want to speak of you as well?
Yes, if I can do speak of you on here and just the thing on there, that would be cool. Bear with.
I don't know which side it is. Above. Is this it? Okay.
Yeah, that's all. Cutting off a bit off the head, that's all right.
Where am I? Am I close? There you go. Cool. There you go.
Cool. Hello, everyone. This is slightly different from the talk that you've heard before, and probably slightly different from the talk you heard afterwards, because this isn't going to be about code so much as a story. And this is, oh, sorry, I'm mic'd now. This is like my story of how I got into open source, which I've been doing for quite a long time, and it's brought me much joy. And one of the things that has occurred to me, like over time, is that I was quite nervous about getting into it in the first place, and actually, I'm glad that I did. I'm glad that happened, and I want to reduce the mystery, and that's kind of what the aim of this talk is. This picture, by the way, is me in Orson Welles, which is a very fine film directed by Richard Linklater. I would recommend pretty much anything that guy has done. Yeah, particularly the Before trilogy. That's just by the by. Yeah, so let's get into it. Yeah, as I've said, I'm John. I blog. I do open source. I tweet a bit. I toot a bit. That is the term, I think. And it's yeah. Who knows where that's gonna? Who knows where that's gonna go? We're all watching it with interest. who knows? I work at Investec. I'm an engineer there. Yeah, my focus is on is increasing engineering effectiveness, and it's a cool place, and we're going to start doing some open source there too. But yeah, this is more about all the things that I've done outside of work. And to tell that story, we're going to go a little bit like further back. By the way, I'm totally aware that I'm so the oldest person in the room, probably. Like so many of you, like super young, it's amazing. And now we're going to see what I look like when I was super young. So this is me when I was 8 years old. That's me on the left-hand side there. And we're looking at this because this is, yeah, that's my brother David and my sister Kirsty, by the way. You're looking at this because this is when I first got my hands on a computer. So way back then, like the typical thing that you were given, or it was was an Amstrad, or at least I got an Amstrad, and I spent a lot of time like typing in like computer listings and stuff like that. And so yeah, I totally rocked 10 print hello world, 20 go to 10. Yes, back then programs did have 10 and 20 and things like that at the start of their lines. It was just the way that it worked. So yeah, Dad bought a computer when I was 8 years old, and I did some like programming then. And then when I got older, I did computer science at A-level, but I was like, don't know if this is what I want to do. I went off and did something else at university. Turned out actually I really like computers. And then when I got out, I got a job, and this is me like about 20 or so. And like my first job was writing in a language called Delphi, and that probably doesn't mean much to most of you, but like Delphi was kind of like Visual Pascal, and it was an Anders Hallsberg joint, which is definitely relevant to all of you because he is like Mr. TypeScript, or at least one of the, actually that's unfair. There's many people who could be Mr. TypeScript, but he is clearly like a very strong like force in that. Yeah, so I kind of locked out on my first gig actually because I was learning on the job, doing like telecom software. I didn't really know what I was doing, but I was writing Delphi, and Delphi was just this like, okay, I like this, and I became vaguely aware of like the person who was behind it. I was like, okay, this is kind of cool. Turned out that I was going to end up like sort of like tailing anything that Anders did for like the rest of my life because like everything he touches like turns to gold. And at this point, I was vaguely aware that like open source was like a thing, and like you'd read articles in the paper every now and then saying, is this going to be the year of like Linux desktop? And they're still writing the articles right now, so. But yeah, like I was aware that like open source was there in this thing, and it seemed kind of like interesting and exciting, but I didn't know like how one got into it or like in what way you like connected. It was just like it was an unknown. So like I was yeah, tootling along. Like I went and worked for Microsoft for a bit. I worked for a marketing company for a bit, and like many people in London, I've done like a lot of work in the finance world. Like this is the big local employer, like finance, and yeah, so I've spent like yeah a long time working in that kind of field in a tech aspect. Now, like around about like 2008, open source started to go like really mainstream. That's when like GitHub like hove onto the world. This is their original like logo, GitHub social coding. I'm so glad that they dropped that tagline. So when that came out, that was like it was the big times of like Facebook and Twitter and whatnot. And I think they were weirdly trying to sort of like connect themselves to that, even though it's either way. That was when I started to see that like the open source was like a thing that I could understand. It's just code. Like there's no mystery here. It's just code that someone's written, and you can be part of that. You can interact like with that. And yeah, that was like a revealing thing like for me. And I started also to see things that were like tangible and things that connected with what I was doing. So I was in a very like Microsoft-y like type ecosystem, and they started to like put out things that were like open source as well. So like .NET MVC was like a big deal, and this was like open sourced, which was like a very surprising thing for Microsoft back then. Because back then they were like super why would they do anything like that? They've been closed source everything, and also like jQuery was like a big deal. And there was a hand up. I thought it was a question. Fair enough. Yeah. Exactly. Yeah. So yeah, jQuery was it was a delightful thing for me too, because I'd started using like JavaScript in my first job, like sort of without knowing it. And like most people like back then, you didn't really learn JavaScript. You just like, it was this thing that was there, sort of like a scripting language. You didn't really know like how it worked. It was just like there. And jQuery, like that was the point at which the world started saying, okay, no, we're going to build like real big, like web applications. This is going to be a thing that's going to be like massive. And jQuery is the thing that kind of made it happen, because instead you didn't have to do like, this will age me, if document dot all this, else that. You didn't have to do all this kind of stuff. You just had like a simple API that you could use that allowed you to like interact and like do things like with stuff. You could build stuff. It was brilliant. And it was also like really just compelling to see that there was, here's this thing that like this one guy like John Ressig had like done, and like other people were like contributing to it, and it's like, oh, this is a big deal. This is awesome. So I always started to feel like this is for me, or maybe this is for me. Maybe there's something here that I could be part of. I was keen. I had a hunger for something, but I didn't know quite how I could fit into it. And now we're going to go forwards in time again, and now we're going to go to 2012. Hello world. So this is me, like a proud father, and that's my boy Benjamin there, who has just been born. And it so happens that the 2012 was not only the year that Benjamin was born, and okay, isn't delightful. It's also the year that I chose to like start blogging and start doing open source, and I don't know if there is a connection between those two. But that is like when things like started to happen for me. So I've been wondering all this time, like how one like didn't. I sort of like was expecting maybe someone's gonna like invite me in and like, here's how you do it. Here's the thing that you do, and no one was. So at some point I just sort of thought, okay, I'll make it up. So like I started, I fired up a Blogger, and had like a blog on Blogger, and like the what do you call it, the highlighting, syntax highlighting looked awful. In fact, it didn't have syntax highlighting initially, and because I couldn't work out how to do it, and then lots of stuff like that, and also like I was like, okay, GitHub's there, and like I could do an open source project on there, and I had like a few ideas of like things that occurred to me, so I did my first open source project. And if you look out, clearly naming things is hard. jQuery validation unobtrusive native was the name of my first project, and yeah, it's a mouthful, but it was really cool. And it was, yeah, like everything that I've done, like open source wise, has been JavaScript / TypeScript related. And this was like still is the case now. People are building forms. This was about helping people build forms, and like I could tell you more about it, but it was yeah, I don't want to burn time. It was connected with stuff that I was doing at work. So that was actually often a motivator for things that I was doing. So whenever I was doing something at work, and I'd see something, it's like, okay, this isn't just like useful for what I'm doing like right now. This is like generically useful. This is something we could like use like by and large. I'd note that down and potentially consider like how we can like take this and do something with it. So this is just like me doing something like by myself, and like it's still out there, and weirdly people are still using this, which is kind of surprising because I haven't touched it in like 6 years, and I've put a big notice on it saying, you know, I'm not touching this. And but yeah, people are still using this. More significantly, I started contributing to other open source projects. And as I say, I was like super daunted about like how I could like contribute to open source projects, because like people just gonna like laugh me out of town when I submit a pull request. I was like really like nervous about it, like real like imposter syndrome. I was just like, this is not gonna, I don't know. I don't know. I had the expectation of like of self-harm in some way, shape or form by putting myself out there, which was mistaken. But you know, you don't know that until you know that. But what I did realize as I used other people's projects was that the docs were often like not great. Like you do something and you're like, this doesn't, like, the docs don't tell me this, or it's actually slightly different to this. And like I could, and everyone like still hates doing docs. So yeah, in fact, if you can get like ChatGPT to write, they probably can write docs. I would start submitting like docs PRs to AngularJS and jQuery validation and things like that. And actually they would take my docs PRs by and large, and I was hugely encouraged by this. Like in fact, it was like 2014 or something. Like there was like ngconf. Angular was like massive then. Like everyone had this like big event in Paris, and part of it was they brought up like all the people who contributed to Angular 1.3, I think, like in a big like picture on the stage. And I was like, and my profile picture was in there, and like all I'd done was like one line in the Angular router or something like that. But I was really pleased by that. Like it really bolstered me. I was delighted. It gave me confidence. And I also started working on Definitely Typed. So definitely typed, you probably know, is the place where you go to get like type definitions for things that like don't ship their own types. And it's been like, it was started by a guy called Boris Yankov. Yeah, it's last time I checked, it was something like the 8th or the 7th most active open source project like in the world. Like it has a lot of activity because like it's typing like the whole world by and large. But back then it was like nothing. Like it was like 5 people working on this thing, and I was working somewhere and I was using jQuery because everyone's using jQuery, and I was like, jQuery is like cool, but like when I'm using it, like it should be better than it is. Like I want to have like a first class experience when I'm using jQuery. I want to be able to like dot into this. I want to get the IntelliSense that like just like best in class. And I decided I was just going to do that. So like day by day, I'd like submit pull requests to Definitely Type to get like jQuery like to be a better type definition. And like Baz, who was one of the maintainers of Definitely Typed, he would describe it as like me DDoSing Definitely Typed, to the point that he's like, okay, why don't you just join and just like do stuff? And I was like, great. So I did, and I carried on for some time, and I ended up actually writing kind of like the history of Definitely Typed, which to entertain myself, I do so many things just to entertain myself. I call Definitely Typed the movie, and it's a good story. And I don't have enough time to to tell it right here, right now, because it's quite a long story. But it's kind of the story of like from the beginning of like TypeScript up until TypeScript 2.0. By the way, TypeScript 2.0, at least in my head, is kind of when that's the point at which TypeScript had gone from being like an experiment or a thing that was going to fail to like, no, this is here for keeps, and this is going to be like significant. A lot of people are going to use this, and I can tell. Feel free to like grab me afterwards, and I'll tell you like more about why this were, and feel free to like read the story. I'm so pleased with it. Like it's I had a lot of fun writing. Like I got to talk to loads and loads of people as I was writing. Like got to talk to like, the TypeScript team, got to talk to like Boris Yankov, like loads of people. It's cool. Let's move on from Definitely Typed. So another thing that you quite possibly have used is TS Loader. So I was using TypeScript to like build things, and I was very, very happy with them. And then at some point, like we went from like everything being globals to okay, we're going to use modules, and there was this thing called Browserify, and I used that. And then this thing called like Webpack like hove onto the scene, and Webpack was just like, so it was kind of like Browserify, but just like a bit better. It seemed to be. Hopefully that's not controversial. Anyway, and I was using that, and the way that you took like Webpack, which basically did like JavaScript, and plugged TypeScript into it, was with a library called TS Loader. There was also like another one around at the time called Awesome TypeScript Loader, and there may have been another one too, but either way, I was using TS Loader, and I was really happy with it. I didn't really think too much about it. I think I may have submitted like a docs PR for that. But like one day, TS Loader went red. So like I would like keep an eye on it like here and there, and like one episode went red. Basically the status badge with, I can't remember what the source control thing was back then. Yeah. Either way, like it went red and it kind of stayed red. And I had this like nagging feeling in the back of my head, like it's not good that this thing's like red. Like you want this stuff to be working. And I had like a selfish reason for this also, which is that like I really liked writing TypeScript. I didn't want to stop, and this was before TypeScript 1, air quotes. This is the point where you had to like convince every single person like we should use TypeScript, it's a brilliant thing, and it was a hard conversation every single time. But like I was relatively good at persuading people, but like I could only persuade people when like stuff was like demonstrably working. And if you've got like an ecosystem where things are like broken, it's like, oh, that's going to be a problem. So I was looking like with great nervousness at this broken thing, and like, well, what do we do now? And it stayed broken for like 3 months or something. And then I realized something. So there's an organization on GitHub called TypeStrong. And it has lots of like TypeScripty like things in there. So TS Node you've probably heard of, it's there. TS Loader, it's there. Fork TS Checker Webpack plugin, it's there. Loads of things. And I happens to be an owner of TypeStrong, not because I've done anything else, because I hadn't, but it was kind of started up by Baz, who was like one of the people who worked on Definitely Typed. And Baz is a serial get involved, check out person. He might be watching, hey Baz, and he would say that too. And so he was very good actually, yeah, jokes aside, he's very good at empowering other people, getting other people like plugged into stuff. And he would like get people like plugged in by just like adding them as maintainers. And so I long story short, I had the ability to do stuff in the TS loader space, and someone had already opened, it turned out, like a pull request that would like fix the thing, and it was just like a Node API thing. So like Node 6 was about to ship, and the API changed for like file reading or something like that. It was that, and I was like, oh, someone else has done the work. Like I could merge that thing. I have the permissions to merge that thing. And so after umming and ahhing, like I raised like a meta request on TS Loader saying I might be able to help with some stuff. I was very guarded in what I was offering to do, and I merged the pull request. And I wasn't too sure what was going to happen next. Like I'd done something, but I was like, who knows? And the thing that happened next was that James Brantley, who was the person who started TS Loader, I think, he he tweeted this: "My open source guild has been lifted thanks to Johnny Reilly stepping up to take over TS Loader. Thanks, man." I hadn't. I was like, don't know about this. But anyway, he gave me npm publishing rights, and I was like, okay, well, I've got publishing rights, so I'll publish type TS Loader 0.9. so I did that, and then turns out that I broke some stuff. So then I did like 0.9.1 to fix the stuff, and but I'm like, so I've got a thing out there, and like I had the thing that allowed me to do my day job, which I was delighted about, and it was like, this is really cool, and I could also see like loads of things that were like reasons why James was not having a good time. So James, basically, I think he kind of like burnt out at this particular point. And by the way, burnout is like a super serious thing. You should take it seriously. And yeah, he was like, I can't do this anymore. But it so happened that I was able to like spot a number of things there that you could like do to like improve quality of life. And it was by the way, it was like a more primitive time. We didn't have like lock files then and that kind of stuff. So so that kind of like added like an extra stuff to the carnage. But yeah, like I started just like playing around with it, doing stuff. I refactored it. Like it was one file originally. Like I split it out into like modular things. I wrote a different test pack. I made some changes to the way that the existing stuff worked to make them like less brittle. Just got going with it. And TS Loader, as you may or may not know, like carried on like quite well. So it went from 5 million downloads per year when I picked it up, and it's currently at like 270 million downloads per year, which is quite a large number. And it's used by like lots of people. It's used by Bloomberg, Investec, Microsoft, Google, probably Cloudflare, I don't know. It's used by loads and loads and loads of different people. That's the point. Like I don't know. People are just like npm installing and off to the races. And yeah, it's, by the way, we are in the third age of JavaScript, as Swick says, and like people are doing stuff with like a Vite and stuff like that. So I do kind of expect. I mean, I'm kind of amazed that it's lasted this long, right? Like JavaScript's supposed to be like everything dies in like 2 days, like it's like the life of a mayfly. So I'm kind of amazed that it's lasted as long as it has, but it has. We're probably going to start seeing a tailing off as like the third age of like Go Rust powered type things like appears. But it's yeah, it's kept us going for like in the meantime, and I've been delighted to do that. Now you might be like wow, it's amazing, 270 million downloads, so incredible. Like it's probably like I'm not the best engineer. I'm genuinely not. And like, if you're feeling like I'm an okay engineer, but like clearly I don't have much to offer, like you shouldn't feel that way. You shouldn't feel that way. Like it's like I'm a good engineer, like I can rock fist bus with the rest of us. But like and I work hard at communicating. I really enjoy communicating. I'm curious and I'm enthusiastic. Hopefully that shows. But like and I think that's probably enough. That really is enough. If you're thinking about like contributing to something and you think you're possibly not adequate, like I would say dismiss those thoughts, because like you more than are. Like just get stuck in. Like what did like open source do for me? Fun and profit, obviously. Like I did have fun. I do have fun. Like I like building stuff. I really enjoy like doing stuff that I know makes like an outsized difference to lots of people. So like I make a change to one thing and lots of people are going to be using this and it's going to improve their days, and I get a kick out of that. Like brilliant. Profit, like yeah, I mean like in kind of way, like so it's led to work that I wouldn't have had otherwise. It's led to relationships, which is a kind of profit that I wouldn't have had otherwise. Hey, I probably wouldn't I wouldn't be here necessarily like right now if I hadn't like done this sort of stuff. Like one thing often leads to another thing, and I would encourage, like, you never can like do like a big journey thing, but if you do like one thing, that might happen to like another thing, and it's worth pursuing. It's like if you're thinking about like OSS, like there's all kinds of things you can get out of it. It helps you to like build your brand as an engineer. It allows you to communicate. It allows you to to collaborate with all kinds of like cool people. You get to meet people that you wouldn't otherwise have done. I've got to know all kinds of like really cool people like, as a consequence of that, which I've been delighted by. At Christmas time, I went for a walk around London with Andrew Branch, who's part of the TypeScript team, and that probably wouldn't have happened if I hadn't done stuff with like with open source, like all these like cool things that can happen, these human interactions as well, like totally worth like seeking out. So we're kind of at the end of my my spiel, my talk, and yeah, I thought I'd hijack Lord Kitchener here and say OSS needs you, but it's to be happy. Like I'd say if you're thinking about like doing OSS and you've held back from doing it, like don't hold back, like have a go. But also like enjoy yourself as you do it. Don't do things because you feel like you should, but like I'd say like if there's a thing that you think this could be interesting, this could be good, like have a go. And that is me. It's been lovely talking to you. Oh yeah, questions. Yeah.
John, any questions? Hey, Andrew Booth from Cloudflare. So this was kind of the theme of your entire talk, but you started by saying there's a lot of younger people here. If you had to give yourself one piece of advice 20 years ago, aimed at people in this room generally, what would it be?
That's really good. Don't wait. Like, yeah, don't wait. Just do stuff. Like, and it doesn't matter. Yeah, failure doesn't matter. Like, it really doesn't matter. Just do stuff. Put stuff out there. It doesn't matter if like stuff is successful. Just do stuff, and cool things will happen as a consequence. Yeah, don't wait. Thank you for the question.
Any other questions? Hi, here's the presentation. Open source contributions can take up a lot of your time, which can be quite painful when you've got a software engineering job.
Yeah.
I'm curious as to how you managed it, because it seems your journey really took off not only when you were fully employed, but then you had a family. So
Yeah.
you didn't really talk about that too much. Did you try and work that into your professional life, or did you try and make time in your personal outside of employment life?
Yeah. So this is a funny one because I don't know. I can't really recommend this aspect of my life, which is that I'm not a great sleeper. So much as I would love to be able to like sleep into like the halcyon days of like 7 a.m., I don't work that way. And I tend to wake up most mornings at 5 a.m. And when you're like awake at 5, like actually like a really healthy thing to do is go out for a walk, and come like 6 months of the year, that's what I'll do. But like, hey, it's dark right now, it's winter, and it's like that 6 months of the year. So I generally have like about an hour to like an hour and a half at least every morning when I'm just kind of like by myself with not much to do. And so I would do a lot of that stuff then. So yeah, yes, I'm so super. That's not a great answer. that's kind of what I've done. But like, I also do stuff like I do stuff like it like in the evening sometimes as well. I try to, because of the sleep thing. Actually, I try to resist that because the later I code, the less well I sleep. But I'd say don't force it. If you find somewhere in your day where you've got like a couple of minutes to do, it doesn't have to be like I will do like this amount here. Like I just like do bits and pieces here and there. Like I ship sometimes, and like if you look at my GitHub history, you'll definitely see that sometimes I do a lot, sometimes I do a little. So like Christmas time, I actually I played with lots of things over Christmas that like just like things that occurred to me. Like here's the thing actually, by and large, I work on the basis of like, here's an idea, it will be cool to play with that idea, and like I do stuff there. And rather than like I'm gonna make myself do this thing here, like I follow my curiosity, and that's a good thing. Yeah.
All right.
You touched on burnout briefly, and I was wondering if you had like some more thoughts on how to kind of reduce burnout, or how to like start working on projects you're passionate about, especially given that you know, if you do software development as your job, how do you find the motivation or passion to do software development, you know, outside of that?
Is that good? Are you streaming?
Turning it off and on again.
We're good. All right. Hello, YouTube. Okay. Hello, everybody. Okay. Are we ready? All right. All right. My name's Alistair. I've somewhat organized this event with Simon, who has just gone. Oh, he's there. All right. Just real quick, can we get a round of applause for Simon because he's an absolute legend. This would not have been possible without Simon. He has helped in like every single part, and I've just given random, spontaneous phone calls. So thank you very much. He's a hero. Okay, so if you've been on TypeScript Twitter, which I'm sure most of you have, seeing my tweet to be here, you've probably seen Zod, which is a library for doing data validation at runtime, and it has very good types. It's made by a guy called Coll, who's an absolute legend, and he is just a full-time ride-or-die TypeScripter. And Zod was based on a blog post, which I can give you guys a link to. I don't have it in this slides, but it's called Pass, Don't Validate. So I'm basing my talk off that blog post. So who am I? I'm Alistair, software engineer. I do enjoy open source, and hopefully one day to the degree of John. It'd be cool to have that many million downloads of packages. I'm a dropout, so I left school in year 10, and I don't have any qualifications. And this is the first time I've ever organized an event, and the first time I've ever done a speak, so I hope this goes well. Thank you. I'm on Twitter, as I'm sure you guys have found me, and also on GitHub at Ali. I don't have a SoundCloud. So this is Pass, Don't Validate. Write 100% type safe and reliable TypeScript. So first of all, what is Zod? Why would you need it? So imagine you're building an application, it's a server-side framework, whatever it is, and you have untrusted data from a user, like a login form. You want to make sure that the data that's going into your application is totally valid, secure, in the right format, no unnecessary properties, etc. So it's safe to insert directly into a database, basically. This is really important because if you have unexpected data, you want to make sure it's in the right format that you're expecting. You can make your apps more reliable, and you can make guarantees about what data you're using and design a contract that says, I expect this data, I expect a user to look like this. If someone's sending me a user, I need to make sure that it matches this exact shape. It's also useful, for example, if you're querying external third-party APIs, and maybe you don't trust the provider so much. So, for example, if it's like a very small company, and you don't know if they're going to change their API definitions, whatever that is, then you can verify that your requests come back to an exact shape that you're going to guarantee, and make sure that your code won't fail, and you'll have properties that you can't access, etc. So here we have Visual Studio Code. I don't think this is going to load. Okay, it does, awesome. So we have a bit of JSON here. It's just some text. You can see there's my password that I do actually use for every single one of my accounts. So I haven't got to obfuscation yet. There's my name, my email address, my password, and then we have a little bit of, imagine this is from like an API, like a GET or something. Very insecure, shipping my password back on a GET, but whatever. And success tree. So we don't need success tree, right? This is just unused data. So let's have a look what it looks like to do this in an unsafe manner. So we can JSON.parse our response body. So this typo is uncaught right here. Like we can't access name. That's not anything on our JSON. We can access success, which is kind of unnecessary. We're polluting our DTO, which I've had some criticism for calling that. Phineas at the front doesn't think DTO is a real word, so maybe, I don't know, 50-50. But if you've heard of DTO, then we're polluting that. And we have no guarantees that our email address is going to actually be a valid email address. So for example, there's an @ symbol that should be in an email address. We don't know that it's going to actually exist, if email even exists anyway. So a safe way to do this is to use Zod. We define a schema for our user, which has a name and an email. And then the email has a .email on it to make sure that it matches the expected format. So first of all, you can pass our JSON. And if we hover over this here, you're going to see it's typed as the dreaded any, which I'm sure you guys will all love. It's the third fire exit in the emergency use case. And we have a user, which you can see is typed correctly as name string and email string. And so when you call .parse on a schema, as I'm sure you guys know, this will be typed correctly. So this is good because our typos are caught, which means that this won't compile, which means we won't be able to write code that will fail at runtime. Reliable code. And we also strip out properties that we don't need. So for example, success is going to be removed. So our actual user object will indeed be name and email. And then finally, we can guarantee that the format of properties are going to be expected and exact. So we're going to make sure that our email is a valid email address. Under the hood, Zod has a regex, and it is huge because I've done some PRs to Zod. The email regex is massive. It has a one for like URLs and UUIDs and stuff like that. We're not going to implement all of those today, but we're going to rebuild Zod from the ground up. So, sounds like a bit of a task. I promise you, this will be objects, strings, and numbers. It's not going to be anything more than that. So we're going to define schemas, which is going to be pretty basic. I did have speaker notes, and I can't see them right now, so I'm kind of bringing this up to the top of my head. But yeah, we're going to define schemas, and then we're going to pass data with them. I don't know what the speaker notes were for this slide, so that's kind of redundant. So there you go, back to VS Code. So first of all, we're going to define what a schema looks like. So in Zod, every schema has a generic, which will be the output type. And if you're familiar with generics, it basically means that we can have just a schema for any kind of type. And it's going to have a parse method on it, which takes in an unknown value, and then we'll return t. Now, obviously, you can't always return t if it's invalid data. So Zod actually also has a safe parse, and I wonder if Copilot's going to write this for me. Nope. So the value is unknown, and then it will return a shape that's more like success true data t or success false. The reason I haven't done it in this talk is because I don't have the error type, but if you've used it before, that makes sense. We're just going to implement parse. And so, for example, let's say we wanted to write a schema for a string. So we're going to say const string schema is a schema for a string, and then we're going to implement a parse method, which will take a value. We're going to say if the type of value is not a string, we're going to throw a new error and say no. Otherwise, we'll return this value, just like that. And so all of a sudden, we have a string schema that can take in a variable that we're going to pass in. This could be the email address, the username, whatever. It's not very useful. There's not a lot we can do with it, but we will get a correctly asserted value out that will be a string. So if we called string schema.parse on this string, we know they're going to get the exact same value out. If we called it with 2, it's going to throw an error. It's going to say no. In Blue Peter style, here's one I made earlier, basically the exact same thing, except it's a function, and there's a reason for that, and we'll come on to that in a minute. This then returns the schema rather than it being a schema itself. So next slide. Okay, so all schemas implement the .parse method, as I just showed. And in Zod, schemas are broken down to the smallest possible primitive. Obviously, you can't for things like objects, but you build up with the primitive values in Zod. Most commonly, you'll just use an object and pass bodies or whatever. But yeah, so the smallest schemas is what we're going to write today, and then we're going to do an object, which is kind of more complex. So what's next? There are 3 things that we're going to cover. The 4th one is kind of important, it's definitely important, but out of scope for this talk, is error handling. There's a whole lot to that I actually talked to Colin about, and it's kind of out of scope for this talk. But definitions, which is a feature of Zod, the infer type, which is another feature of Zod, and also objects, which is more complex than just a basic primitive type. So definitions in Zod are a way of defining a string, for example, and then saying, I want this string to be minimum of 3 characters, maximum of 14, conform to this regex, and all of a sudden you have a valid username. Or you can say a string that's an email or a URL. They're basically just attributes to the schema that say what this is actually going to return, what's it going to pass. It's just more information beyond just the type. So for example, there you go. Is email, is UUID, minimum, maximum, etc. We're going to implement a few of these today. So here we go. Here we have our schema. Okay, Copilot's asking me to sign in. I'm not going to do that now. Oh well, that's annoying. So we have a schema that has our out. I've renamed it to out just because that is what it is in the Zod code base. And so we have a number schema that's going to extend a schema. So we're going to then write const number, and this is going to then return a number schema. And then we're going to do return pass, which is going to take our value. If the type of value is not a number, throw new error, and you guys can guess it, no, just like that, return the value. And all of a sudden, we need to then implement our min method, right? So min is going to take in a minimum, and then it's going to return number again. Now, this is kind of useless because we actually don't do anything with the definitions yet. So we will come on to that in a second, but then we're going to return number again, and then same for max. I'm just going to copy this, just like that, and then maximum. And so to implement a definition, the reason that we call this as a function is because the first argument to our function will be the definition itself. So let's say we have type number definition, and then it has a minimum, which is a number or undefined, and it has a maximum, which is a number or undefined. Thank you, prettier. So then we're going to put our definition in here. We're going to make it optional because we don't want everyone to have to specify it. Not optional, so we're going to give it a default. And then we're going to say that the minimum is undefined, there's no minimum, and a maximum is also undefined. And so all of a sudden, you can see that when we want to add in new features, we can spread out the previous definition, and then we can add in the minimum as our new minimum. And so this is useful because it means that all of the schemas are totally immutable. If you add new methods onto a schema, it's not going to affect the one you just edited. This was a big thing recently, if you guys know about Moment and Day.js. Day.js was immutable, and so people preferred that. And it just caused a bit of a headache. So we do the same thing for here. So def, and then we have maximum, and that's the maximum, just like that. And so then in our pass utility, we can say if we have if value dot, if def dot max, we can then validate in here. We can say if value is greater than def dot max, we can then throw our error no like that again. So that's basically, this is obviously poor code, I can inline this, but that's basically why you'd have definitions. So here's a string that I made earlier, again in Blue Peter fashion. So it's our string schema, has a minimum and a maximum. In theory, I could have added support for is email and is URL. No, I didn't in this one, that's why they're not there. So there's our minimum, there's our maximum, and you can see that it just spread out the previous definition and add in the new values. So that is why we need a definition. I hope that makes sense. So definitions allowed us to write portable schemas that can be cloned and remain immutable, and they follow what's known as a functor pattern, sort of, if you're familiar with that kind of functional programming. So what's next? We need to create the infer type, and we need to create an object type. So first of all, pop back into VS Code. We have our new schema, and all of a sudden we now have our infer type. Now it's typed as any, which I'm not going to leave it as, obviously. And we're going to say if the T extends schema, we're going to infer our output, then we're going to return the output, or we'll return never. And so all of a sudden you can see, it's actually a question mark. And all of a sudden you can see that our output is now all of a sudden one word or string array. Now this is a very odd schema. I don't know why you'd ever want to output one word or a string array, but proof of concept. And so this is useful because if you're familiar with using the infer keyword, we can then take a schema type as an input to this type and get the exact output, which is very nice for whenever you use z.infer. So that's the infer keyword done. So now we have all of the primitives. We need to build more complex shapes. So now we're going to put an object together. So hop back into VS Code. Here's a very big number schema that I made earlier. and has things like positivity, and it has, if it's an integer, the maximum, the minimum, etc. And then here's the implementation for adding these functions, these methods onto it. So again, spread out the previous definition and add in our positivity, or the is integer, etc. So integer makes it an integer. And then so here we have another string that I made earlier that has support for email and URL. And so you can see there's a definition for it. The minimum is 0 because obviously string can't be below 0 in length, and the maximum is undefined. And there we have, here you go. So this, just a bit of information. Obviously this is not a proper email check. I'd use a regex. I was writing this at 4 in the morning and I haven't slept much. So lessons learned, do your first talk in 2 weeks in advance, not the night before, but there we go. And then again, more loose validation, check it's a URL. Obviously URLs don't have to start with HTTP, it could be whatever. So here's the email. And again, we can check for invalid state at this point. If this schema is already checking for a URL, we can just say, nope, you can't do that. Again, for checking for a URL, you can't have a URL, it's also an email. Minimum, maximum, that makes sense. And then finally, we have an object to build. So this object, I'm not going to write it out now because it's much bigger component, but we have our object schema. Now there's no properties in here. I was planning on adding in more, but I think it's out of scope for this time, so just ignore that. This could just be schema and not have to write that all out. And any object shape is basically saying we have a record where the key could be anything, right? That could be user, email, age, password, whatever. And then the value of that is going to be another schema. And so this is the input to the object. When you call the object function, this is the input shape, which will just be a record of schemas, basically. And then to define our output, we then loop through our shape, which is t here, and we then infer what that schema resolves to. If that's another object, then it's just fine, it's recursive. If it's a string, this will be a string. If it's a number, etc. Notice I haven't done booleans in here. I just thought string and number would be enough, but obviously boolean is another primitive you could use. So here we go, here's our pass function. If it's not an object and the value is null, well, we don't have an object. Otherwise, we have our result. We loop through the keys of the shape. If the key doesn't exist in the value, well then, this object's invalid. And then we reassign to our result. We take the schema that exists at this key. We pass it with the value at this key. And then that will return. If that fails, then it will throw. If it doesn't fail, then the result is now the correct object. You'll notice that this also strips out unused properties. So for example, if there's no success in our schema, then it will obviously fail. And then we type the return value to be, again, infer out. So this could just be then the infer type here. So that's the object type. And then we can check this works. So we can say const user equals object. And we can say username, string, and then we can say age, number, like that. And then what we can do is user.pass, whatever, and then we have age and number. And age is a number, and username is typed correctly as a string. And because these are the primitives that we defined earlier, we can still add, for example, min, like 2. And on the age, we can then say min 18, which I'm only just, so I can go to the pop after. And then, yeah, so that's the objects. And if we ran that, that would run correctly. Oh, sorry, it wouldn't because we have nothing in there. But if I added the right properties in here and said age 19, then obviously that would work fine. So the title of the presentation is a little bit kind of irrelevant. Pass don't validate basically means to retain type information when you're passing, when you have some data. And it means transforming and returning the new shape. Validation, in my eyes, it's kind of only specific to type languages, functional languages like Haskell and TypeScript. But imagine that you had some random data, rec.body, for example, common pattern in Express, Fastify, rec.body, whatever. If you then just validated the type, you'd still be using rec.body afterwards. It would just say, does rec.body meet this specification? Does it meet this contract? Does it have user, email, age, whatever? And if it doesn't, then you can throw and return, end the request. If it does, you continue using rec.body, so you can't have access to any transformations. The type information is not retained. Whereas to pass sort of means to pass rec.body into a function, and it will return the actual shape. I think that's the difference, and that's the blog post that Zod was inspired by. And so to wrap this up very briefly, so Zod is built up on primitives. Schemas contain definitions that allow them to be totally immutable and copied when mutating. Parsing should retain as much data as possible and return it, rather than just checking and returning a boolean for is valid. And implementing a standard schema T allows schemas to be portable and quite literally generic. So any questions? Thank you very much.
questions?
This is not. What's the VS Code TypeScript extension that you use? It looks pretty. I like it.
For type, which part?
The thing that annotates the errors.
Oh, the errors. That is called Error Lens or something. I can send you a link to that. It is pretty cool, to be honest. Yeah. Any more? Yeah, that's pretty cool. Awesome. Okay. Thank you very much, guys.
Thank you very much.
Okay, nice. I'm Andy. I'm the CTO of this company called Bobsled, which we started about 18 months ago. And I know Ali, so he invited me here. And one of the first things I did after deciding I was going to start a startup, at the time I was working at Neo4j, where I was a Java engineer on the clustering team. I had been on the database as a service team. First thing I did was call Ali and say, I'm starting this business and we're going to need to make a SaaS product in the cloud. It's not going to be a Java monolith. And that's all I've done for 5 years. So what are the cool technologies that developers use these days that I need to be using? And he reeled off a great list. He said you use Vercel and Next.js and Cloudflare and Prisma and a bunch of other things. And I was like, whoa. But like, where do I start? And he's like, well, TypeScript. Good starting point. Threads. That chimed with my experience going back. So when I was a lot younger in my first job, I was doing C# and I remember this Node.js thing came out and you could suddenly run JavaScript on the server. I was like, well, I spent all my time writing client-side JavaScript and sometimes C#. Like, why can't I just write all the time in JavaScript? That was pretty cool. And then a couple of years later, I heard about this thing called TypeScript. And since my boss at the time said, no, this server-side JavaScript thing isn't going to catch on, I'd stay away from that if I were you. Let's just write JavaScript for the browser. A little bit later, I remember when the first version of TypeScript came out and I went back to my boss, still at the same company, and said, look, we use C#. The same kind of guys have made this TypeScript thing. It seems pretty similar. Wouldn't it be great if we started using TypeScript just on the client side? And he said, well, I'm not sure. I think we should wait till 1.0 and see what happens. So I moved on to a different company, wrote a lot of Java instead. Thought I'd learn some new things. I went to Cupertino, the company that I was acquired. I came back to London after a while. I had a startup where I was the head of engineering, and same transition. So I had been writing Java, went to a company, needed to do something faster, something a bit different. I was like, I'll try Node.js. I think that sounds like fun. Seems to have caught on a bit. But writing JavaScript coming from Java seemed like a bit of a pain. I heard about TypeScript. I tried it, felt a bit slow. I was under a lot of pressure, so I wrote a load of CoffeeScript. About a year and a half. Any CoffeeScript fans? Yeah. So that's pretty much my hiring experience at that company when we raised Series A. And we managed to hire some engineers after raising Series A, and probably about 2 or 3 weeks in, one of the senior engineers I hired kind of took me aside, got someone else, said, we need staged intervention. We can't keep developing this in CoffeeScript. We need to switch to TypeScript. So at that company, we ported everything to TypeScript. It didn't take us very long. It takes about a week, which is pretty good. We obviously did some of the tricks everyone knows to start with more flexible types and a lot of any everywhere, and then backfill until it was all working nicely. So yeah, when Ali said you need to do this thing in TypeScript, I'd already had that experience before and I thought, okay, let's do this in TypeScript. It seems to work. And now I can hire engineers. It'll be great. So at Bobsled, I said what we're going to do is we're going to use TypeScript, and we're going to be a TypeScript first company. So we're not just going to use TypeScript in the browser. We're not just going to use TypeScript on the server side. We're going to write our infrastructure as code in TypeScript. We're going to write our bash scripts and our deployment scripts in TypeScript, and we're just going to do everything in TypeScript. And that way, it will be great. So this is some of the stuff that we've learned and picked up by taking that approach. And I'm pretty proud that what we have is in our repository is almost exclusively TypeScript. There's a tiny bit of Terraform and there's a tiny bit of Bash, but we are TypeScript first. So TypeScript first, we have used strict and all the types on everywhere. We dislike any as much as probably most of the rest of you. So these are some of the examples of places where we have had to come up with some tricks to do end-to-end type safety. So browser to server or client server communications. I'm sure people are familiar with TypeScript may have seen drama related to whether or not you should type things between the browser and the code. Controversy around DTOs that Alistair mentioned. That's one of the areas, right? We got to go from the untrusted browser to the server, and we wanted to have type safety there, so I'll talk about that. Another place is reading and writing to the database. We use Firebase. It happens. Let's say Ali told me to look at Prisma and look at PlanetScale, look at a bunch of things. I ended up coming back to Firebase in our application, but I've worked on a couple of database startups, Neo4j, and another earlier startup on top of Cassandra. So I've used a few databases and know about this problem of, we've written something to the database, we want to pull it out again. How do we get types attached to it? Then one of my more ambitious projects, right, is getting from deployment time to server runtime. So we use something called CDKTF, which is a TypeScript wrapper for Terraform, and that lets us write our Terraform definitions of our own structure. So storage buckets, projects, IAM permissions, serverless functions, all those kind of things for AWS, Azure, Cloudflare, Google Cloud. We can write those in TypeScript using CDKTF. We wanted to go a little bit further because we realized that at runtime, we need to know lots of these properties that we set at deployment time. And often you'll play around with environment variables in Bash, right? Like, when I deploy to this environment, I set, Google Cloud storage URL, all caps in an environment variable file somewhere. And if I go somewhere else, I change the values. And most places I've worked have built up a sort of craft of these environment variables and things we pass in, and then we start writing config files somewhere and shipping those around. But I wanted to say, when we need to know at runtime, what's the address of this thing, or what identity should I be using, or things like that that come from deployment time, let's make that all type safe as well. I'll show you how we do that. And then the other place we have end-to-end type safety, I've sort of put server to Lambda. Right? So we actually use Google Cloud serverless functions, but Lambda's shorter and fitted in more nicely on the slide, and we do use those as well. There's lots of cases where we want to use serverless functions these days. So we have pub sub queues and then functions that consume off of pub sub queues. We have functions that call other functions directly in a kind of REST microservices style as well. Lots of cases where you want to have functions and other functions triggering each other in the cloud. And those are not running the same process, and there's some data transfer happening between them. I'll talk about how we make those type safe and kind of wrap some types so that we can call a function that might be executed somewhere else, or put something onto a queue and pull it off again, and keep types on those. So first up, we do server to document database. This is why my talk had to come after Ali's, because we use Zod for this. It's a nice example of Zod. Whenever we read or write to the database, right, before we write in our data access layer, we actually check. This is being a little paranoid, but it's nice to be sure that your database contains what you expect it to contain. So in our data access layer, we have methods to write, and they actually parse with Zod before they write to the database, particularly because Firebase is a sort of NoSQL, very flexible document database. This helps us avoid extra cruft appearing, right? And as Ali showed in his example with the sort of is success true, one of the advantages of parsing is we strip off any extra properties that might have accumulated onto objects in our code, and we get exactly what we expect in the database. Reading, right, when we read out the database, we also parse, and that means we get early failure if something really bad is happening. So, if unexpected data is in the database, it fails pretty much immediately on read rather than somewhere deeper in the code that's more confusing and harder to debug. And because of the first point, the second point almost never happens, which is good, but occasionally solutions engineers, or more often me, go into the database and try and fix things manually, and this catches when that's happened. To do this, the main tip is create a data access layer, and I'll show a quick example of that. But this works for all kinds of stuff that I mentioned, right? if you're writing data to storage, if you're writing stuff to files in the file system, if you're dealing with untyped APIs, Zod is really great for all of these cases. Now, I am not as slick as Ali when it comes to this, but here's an example of how we do this. Don't think we need terminal at the moment. Okay, hopefully it's fairly reasonable. This is an example I pulled straight out of our code pretty much of a schema in Zod. All the usual stuff. So here we've got our Zod types, right? Z string, Zod array, Zod other string, and then we use infer, like Ali showed, to actually get the runtime types. Right? We've got enums in here, which we use in a few places. We've got the status, and then we've got this actual object, which VS Code doesn't expand. So we define the type. Then we define our write and read methods. So here, for this flag type, we've got a method to create it, which is not actually parsing in this example. It's a bit naughty. We should. So we should be doing in here flag schema parse. There we go. Right, so now we've parsed the data before writing it into a database. So set doc is the actual command to write into Firebase. So we expect to get a flag, and then this thing we're parsing according to the schema, even though it should be obviously here, but we have more complicated methods where it's needed. Then we write a read method. There's some caching and other exciting stuff going on here. We have implemented this method, which gets parsed documents, but doesn't return failures. So we use this where we're reading from collections, and there might be a few items in the collection that don't parse. And what we want to do is show the user everything that parses, and then throw an error and send some alerts to Slack to say there are some documents in here that don't parse, rather than just crashing if there's one document in 100 that's in some way corrupted. So when we're doing read, we put it through this method, we pass this method the schema and the path to the collection, and everything that's read out of this is everything that parses correctly. And we use that safe parse method that Ali showed briefly, which tells you if something parsed or not, rather than throwing an error. Do that. So that's how we do, in and out of the database. Nice usage of Zod. Browser server. This is more interesting because we don't trust the browser, right? We can't rely on the browser to send us what we're expecting, and that's going to get interesting. But we can trust the server to send the right things to the client. And we use Remix as our sort of framework. It's a server client framework for writing React and hosting and serving React. We actually, on such open source, we maintain a Google Cloud Functions adapter that allows you to run Remix in Google Cloud Functions, which is open source, and we're looking for other people who want to help, if anyone wants to help with that. But anyway, we trust the server to send the right things, but it's quite nice if we can have strong types on the client side. And Colin, who's also the author of Zod, was instrumental in getting a pull request and a change into Remix that allows us to have strong types between the client and the server in Remix. So here you see we've got a loader. That's essentially what happens in the Remix framework when you do a GET request. The loader executes on the server side, and the loader returns, whatever the loader returns ends up on the client. So here we've got a very simple type. We use this JSON, which is part of the Remix framework, to send this back. Then in here, when we do get data, we use this loader data tool, which is part of the Remix framework, and we give it this type of loader, and the type that we get there is correctly typed by the magic of generics. So this is that. Here we have this loader type. When we do type of loader, what we get back here has the same type that we returned from this function, and we can add something else in here. I should let Copilot do that, and now we see we've got our hello in there. Make it const. Right, so hello is nicely typed, and we can, do our get data just to check. There we go. Looks good. VS Code says it's good. So there we've got immediately out of the box, nice types for data that we return on get from Remix. The same is true of things that we get back from a post. So when you send a post request to the server, after it's processed it, it sends you some response. In Remix land, that's action. And what you get back from an action can be typed using use action data. And we've got a nice type on here. This is a slightly more complicated type. It includes, unions and other stuff happening. But this gives us, strong types between the browser and the server straightforwardly and nicely. And this is from our website. So there is a hopefully working localhost is working, and this is from our website. So if you want to know more about Bobsled, you can ask for the white paper. It's somewhat corporate. And this has a form. So we can show an example of how this actually works a little bit in practice using this form, just to prove there's something happening. If I put in my iCloud email address and submit this form, we get back an error saying, please use company email address. This is dealing with data that's been posted. Right. So this is client side, we're posting data to server. This form gets sent into form data. How do we deal with typings on this? Right. We said we don't trust, so we use Zod for this part. What we do on the server is we receive this form data. Right, this is a normal node web standard form data object. This is a normal node request object. And we can parse that with this ZFD form data. What ZFD form data is Zod form data is a library that works alongside Zod. Basically helps you take form data, which is a slightly funny data structure, and parse it with Zod schemas. So we're passing a regular Zod schema here, which looks like this. And this is a little bit complicated. This is a discriminated union. This is kind of advanced Zod, but it's a type that lets you choose between two different types depending on a particular property. The property here is intent. We use this because there are multiple form submissions possible on this page. So on this page, you could ask for us to call a function, or you could ask us to share the white paper. There's two different things, and those, depending on which form you submit, we get different data. So if you ask us to share the white paper, you get the contact form fields, and I am not as good at VS Code. There we go, it's Ali. But this is our Zod form data type for the form field. So first name, last name, email, and company, right? That's what we're going to submit in here. And if we post something that isn't that, we'll get a parse error, and we'll send an error back to the user here, right? So if safe parse is not successful, then we can immediately return error. Hopefully that doesn't happen, but if someone malicious is posting things to our server, we'll catch this. And then if someone actually posts the correct thing, we have a switch statement to figure out which thing they sent us, and this form data then is typing is unpacked because of the magic of discriminated unions, and this is strongly typed, right? Because we parsed it with Zod, and we can send that into the functions that we're going to execute. And yeah, if I don't put a company in here, so I can put Andy at Bobsled. If I don't put a company, it says please enter a company name. We're able to hang that off some of the capabilities of Zod as well. I'm not going to go into that too much, but we can parse those form properties and come up with custom errors based on each of them. Going back to this. So yeah, we use Remix for the magic of server to client typing, and then we use Zod and Zod form data to give ourselves typing when it's coming from the client to the server. Now this is where things start to get a little bit interesting, is we want to have types between our deployment time activities and our runtime activities. So first of all, a huge shout out to CDKTF. This allows us to write our infrastructure as code, which you may have done with things like Chef or CloudFormation, or I'm trying to think of other technologies are. There are a few other things out there. Kubernetes is probably an example, I think a lot. If you use Kubernetes, written a lot of YAML. So there's a bunch of technologies for writing infrastructure code. Terraform is one of them. It's very good. It comes from HashiCorp. And CDKTF is a wrapper to generate Terraform programs using TypeScript. So this looks like this. So we make a stack, and these types are straight up Terraform types here. Don't worry too much about providers, but here we're going and just creating a Google Firebase project. So to say with this type, I want a Firebase project, I set some properties. This is straight CDKTF, pretty straightforward. And now I've got this Firebase project. When I execute Terraform against this, it will create a Firebase project in Google Cloud for me. So I've got a database. It's a good start to having a full stack SaaS application. Then there's some other stuff I can do in here, skipping over a little bit, but say I want to make a Google storage bucket. I just define that like this, give it a name. So there's a Google storage bucket with this name. When I run Terraform, that Google storage bucket will be created. We're actually going to put an object in that bucket, which is the code we're going to run. And we'll create a cloud function using the object in that bucket and Zord Terraform. So we can define the infrastructure that we want to have. In TypeScript, all of these types are strong. So if I start doing weird things like putting the wrong types in here, I'll get nice compile time errors. Maybe not on that one. Right, if I forget to name this function, it doesn't compile. So that's a good sign that we've done all the things right. And yeah, so we can deploy a whole load of infrastructure by writing the CDKTF and then executing CDKTF runtime, which will deploy it. Now, trying to say, why do I then care about having this available? So this is nice, this is strongly typed. The next step is I want some of this information or some of the outputs of this available at runtime. So I've just created this cloud function. What I want to do from my web app is call this cloud function. Right? It's kind of common microservices pattern. In order to call this cloud function, I need to know its URL. And that's an output property of Terraform. So I do this cloud function. Somewhere buried inside here, service config. Right, there's a URI. So this isn't known until after it's been deployed. I might be able to write some complicated string templating to assemble and guess at it. They might follow some rules, but really it's much better for me to say, let's take the output from what gets generated. So this will be populated when Terraform is executed with the output of the URI, which is where Google has decided this function is going to be. And it's going to have some UUID and some other stuff in it that won't be known until deployment. And I want to know this in my app at runtime so I can call this function. So how do we do that, and how do we sort of plumb that through in a way that is nice and strongly typed? What we do is we generate this other stack. Terraform is made up of stacks, which is an output stack, which is slightly complicated here, but what we're going to do is we're going to write some JSON, and we're going to write some JSON using Zod, so that we're pretty confident that it has the expected type. And then at the end of our deployment, that JSON is going to have the type we expect that contains some properties which we want to know at runtime. And we type this. We've actually got this stack output. This is our own class. I think it might be as well. See? Yeah, it's our own class. Does something with generics. And we set the type that we're going to output here. Digging another nice Zod schema. And here, these are all of the properties that we emit at the end of our deployment. And then everything that's set on here, we can make accessible at runtime. And we do that by writing that JSON file, shipping that JSON file, and then at runtime we can read it, parse it again with Zod, and have access to it strongly typed. So have a bit of a wrapper around the code that does that reading. But anything I want to know at runtime can be declared on here. I know it's going to be written. It's going to be parsed by Zod before it's written during deployment. And then I can read it out at runtime. So if I want to call a function, that's not the one, sorry. Here's an example. So we have this function, get environment, and this gets our bobsled environment, and that's the type that I was just showing you with all the deploy time properties, and then we can use the environment, bobsled environment, to get some things like the function URL. Right, so this example function URL will be the outputted URL of the function that we just declared with Terraform. And we can then call that URL, with fetch. We actually have a slightly more complicated way of doing it here, but if I wanted to, I could just call that URL with fetch, and things would all work. So that's how we get from deploy time to runtime with a lot of type safety and confidence. And there's lots of things you can use it for, right? So common examples for that: addresses for functions, database connection strings. We use this for sending our Firebase configuration to the client, because Firebase can be called from client side as well, but it generates a unique configuration in each environment. And so we can automatically wire that up. Addresses for cloud storage, storage buckets. Another thing we use it for a lot is identity to impersonate. So we do a lot of cloud infrastructure management, and we often have to impersonate identities from different clouds. So keeping track of which AWS identity should I be picking up, or which Microsoft Azure identity should I be using for something at a particular time is a pain for us. And we're able to do all that with these nice strong types. One of the other things that we do around this is we actually build for an environment. So some of this stuff happens during our build time. So we set which environment we're working with, we build, and some things get baked in at build time, like this output JSON, and then what we ship has been baked for a particular environment. So another thing we're gonna, how we do this kind of communication, right, is from a server to a Lambda. So we just deployed a cloud function. Now we want to call it, and that function itself has arguments and a return type, and we want those to be strongly typed. So how do we get all of that to work? So we use the address, right, to talk to the function that we got from our deployment. We actually use a service account. In this example, you can see there's a service account to impersonate, which is also being set. So when we call the functions, here they're secure, and so you can't just call it by calling the URI. You actually have to do some authentication. This is wrapping, this invoker GCP function is wrapping that authentication and using this impersonation. Here we mostly trust ourselves, so we don't necessarily need to do Zod parsing for arguments that get sent to our own cloud functions and the stuff that gets returned from them. But we still want to have nice types, so we can do this using generics. We don't have to necessarily go into Zod. So when we call this function, we've got our own wrapper here called invoke GCP function, and it takes as generic type parameter the implementation of the function that we're calling. So if I go to hello world function, get this. So this is the function that I've written and slightly adapted from our production code. And here we just return a type, right? Hello world, it's got time, which is going to be inferred as a number, and magic. Notice here, there's no return type set. So we're making use of type inference, one of my favorite features of TypeScript. We have, in this case, got a Zod type on the arguments that we're passing to the function. This is kind of overkill, but we do it in some places because it makes us feel better, and it's not particularly expensive. So this is actually a Zod typed call. So this function is also written in the code base. When we did the deployment, we have a nice trick going back to the output stack where, not the output stack, the conductor stack. The code that we shipped is from node modules. So our infrastructure as code is an npm package, right? So I have a package that deploys infrastructure. That package has a dependency on another package in our monorepo, which has the implementation of the function in it. And then when we do npm install, that becomes accessible on the node modules path. And when we deploy, we take this thing and we stick it in this Terraform asset, and we use that asset to build a zip of the package. So this is all within our monorepo. We've basically just written this code to say we're going to grab that node module package, zip it up, and ship it to Google Cloud. Google Cloud functions, one of the ways you can set them up is with a zip of an npm package. This means that our monorepo build knows that there is a dependency between this infrastructure as code package and that implementation of the function package, because they're expressed as node dependencies. We use something called turbo repo in our monorepo to build, and because this dependency is tracked by npm, turbo repo can know when it needs to rebuild the infrastructure or not, because we've changed the function code. So not so much about type safety, but a nice thing that we can do there. So we trust ourselves to do all of these things, and we've got this function that we've written We've shipped it into Google Cloud, and now we want to call it and get the return type with strong types. So hello world has been passed on server as the generic type to this. Our generic typing, Ali is probably going to tell me, is much more painful than it needs to be. But we take this function, which is written with this extends, and wraps this other generic parameter out, which is the return type of the function. And then we say that to call this wrapper method, you have to do invoke params, right? Pulls the payload t, which is the arguments type that we pulled off of the function using generics, and it returns the async return type of the function. Right, so we use generics to unpack this function, and the results that we get when we do this is that if we don't use the right parameters, for example, this won't compile. Right. It says this is not assignable to type. So magic. Now it should compile. Excellent. There's also, you might have noticed in here, there's a constraint check that we put on that says this must be assignable to JSON. So you can't sneak any dates or other things in here, because we are going to serialize this and we are going to send it over the wire. And if you try to do something like serialize a date and deserialize it without doing a bit of extra work, it doesn't work. So we've constrained the types that can be sent in this payload as well. So you can't make this work with a function that won't do the data transfer nicely. So we've got strong types there, and the return type has got the return type of our function. So when this runs, it's going to send the call across the wire using fetch and all that stuff. But what we end up with is a nice strongly typed object. And if we change the signature on hello world to return something different, so hello London, actually it's not going to work. Change the property. London. Hello. We should see that this result type now has London rather than hello in the properties. Right, so VS Code has nicely magically tracked all of that for us. I'm going to put this back, otherwise I'm going to get yelled at by ESLint. And on that. So now I've got two things to try. I'm even more of a cowboy than Ali, so I was finishing this up during the first talk, but I'm going to try for a live demo, and we can go through some different steps in terms of live demoing. So first of all, I'm just going to sort of try and prove that all of this works, and go to our careers page. So this is the local copy of the website. Go to the careers page, help us share the world's data. Open positions, we've got more positions now. I didn't quite get that done during the talks, but we are hiring for other kinds of software engineer and SRE. I've added this button down here. It says TypeScript demo. And going back into our remix, here's the action that's going to be called when I hit that button. This is going to call the example function and then wrap the results back to us. So this is the thing we're just looking at with the GCP invoker and all that other good stuff. So this is going to run remix locally on my machine, but it's then going to call out to the function that I've deployed and send something back. And the function we deployed was this thing. So it's going to say hello world and some time. And it's going to take a little while because this is using Google Cloud Functions, and they do use containers, unlike Cloudflare, and so they have cold start. But there we go. So there's potentially premature. One thing I was going to try is we're going to see if we can change this, deploy the function, run the code, and see the change. So we change it to London, hello. I can bring back my terminal. I'm really bad at using VS Code. There we go. So we're going to deploy, new pm deploy environment. Okay, So this is turbo repo. So the script is first building everything with turbo repo because we've changed the dependency. Right, we made a change in hello world. I probably could have demoed it showing full turbo before making a change, but I was a bit late for that. So this is first building all the packages. Synthesizing is creating the Terraform. So the Terraform process has kind of two steps. At first, we run JavaScript, right, a Node.js program that takes all that JS we wrote. That outputs a rather scary JSON file, which is a Terraform program. And then the Terraform program is executed, and Terraform itself is written in Go, and it's binary that's shipped. So that Terraform program executes, and that actually creates the cloud resources. So this is Terraform executing the program that we generated from TypeScript. There's lots of happy messages. There's all kinds of stuff happening here because I pulled this out of our main code. So it's checking to see if there's a Firebase database and all kinds of other things that aren't that relevant to the demo going on here. But nice thing about Terraform is it only makes changes it needs to. So it skips through quite a lot of these because I've already run it once. But we see here, it's told us that it's going to make some changes to this Google Storage Bucket object. This object is the zip file with our npm package, our runtime function. That changed because we changed the source code. So it says, hey, this thing's changed. I'm going to deploy a new zip file. It's going to do some Firebase rules because they need a fix. And then it says this function is going to be updated. This Google Cloud function is going to be updated in place to point at this new zip file, which is the new implementation. Now, Google Cloud Functions are not as good as Cloudflare, so they also take a little while. I'm a huge fan of Cloudflare. I wish we could use it more. I look forward to us getting onto delivering data into Cloudflare R2. But yeah, at the moment, we're mostly in Google Cloud. So while this builds a container and does some very old-fashioned stuff like that in order to deploy a function, I'm just going to riff a little bit. Okay, so we got through that. Lots of other Terraform happened. If we go into Cloud Functions, you can see there's some things spinning because stuff is happening. This was deployed at 20 past 5 last, showing that I was prepared before the start of the meeting with something that worked from the Starbucks, just the other side of the street. And yeah, that's finished. We had a nice full turbo because we do a double check at the end. If I refresh this, it should show, there we go, 7:55. So we deployed our function. Now I can run my local, go back to my local careers page, right? Open positions. And when I hit the button, hopefully we're going to see London hello instead of hello world. Wait, one second. I probably need to restart this because I changed types. Fingers crossed. And otherwise, think of this. See? There we go, London hello. Great, and that is the talk. Any questions?
Thank you very much for that, Andy. Any questions from the audience? Okay, to make it easy on me, you're going to be first.
Hi, yeah, I've just started digging into the TypeScript CDK for Terraform recently as well, so that's really interesting. I'm just wondering where your remix build process fits into that. Does that come sort of last in the process after all the Terraform configuration?
Yes, so the way that we do it is we build and deploy what we call the environment, which is kind of all of the infrastructure, and then we build our applications and ship our applications when we do this for real. So I kind of packed all of that into one stack for this demo. But normally we kind of build and deploy the environment, then we deploy functions into that. And for us, the Remix app is deployed as a function, a Google Cloud function, but we do it after we've sort of provisioned the underlying infrastructure, then we deploy individual components. That also means we can manage different versions and things like that.
If I can just follow up.
Yeah.
So the outputs that are coming out of your Terraform configuration, are they baked in at build time into your remix?
Yeah.
Yeah.
So for us, for most things, we can just bake them in a remix in a build time. There are situations where you can create like a circular dependency, where that becomes a bit more tricky. And what we don't do that because we don't need to. But where I've experimented with it, what we've done is ship the JSON into Google Cloud Storage, and that means you can read it out and have sort of circular dependencies. So you can deploy everything without baking it at build time, and then right at the end of the process, collect together all the information you want, put that into Google Cloud Storage in a like canonical location, and then pull it in, and it's typed and parsed and so on.
All right. Hi, really cool stuff, and the smoothest transition into a hiring page in a talk I've ever seen. If tomorrow we all go into our work and pitch to our CTOs to go TypeScript first or TypeScript only, what's the best thing about it, and also conversely the worst or most painful thing about it?
And the best thing about it is that you can work on any part of the code, and so if you need to implement a feature that touches different things, right, requires a bit of infrastructure, requires a bit of front-end work, requires a bit of back-end or a pub sub queue or anything else like that, it's very easy for one person to work through all of that without kind of context switching or needing to find someone who's an expert in a different programming language. The other thing that's really good about it is because we touch everywhere, we don't have to have any kind of intermediate language things going on, right? So we heard about protobuf and Cap'n Proto. Cap'n Proto is extremely cool. I looked at it a lot when I was starting, but we don't need any of that, or GraphQL, or Swagger, or all those technologies that exist to help you have kind of shared types between different programming languages. So we don't need any of those things. We just write our types in TypeScript and use them. It means that we can develop very fast. The worst thing about it, the NPM ecosystem is a bit of a security risk in some ways. One of the things that keeps me up at night sometimes is thinking about NPM security. So that might be something that your CTO or CSO raises if you start talking about TypeScript and Node being everywhere. Otherwise, the usual pushback is around using the best tool for the job. There was definitely a big trend in software engineering sort of 5 years ago to say, everyone would say, we use the best tools for the job. We use R for this and Go for this and Rust for that other thing and Java for this. And there are good reasons for doing that. And the thing we have is we don't always have the best tool for the job. Sometimes we just make it work in TypeScript, even though it would be better to do it using R or Rust or something else.
All right. Any other questions?
Thanks for the talk. I've got two questions. First one is, having used Terraform a lot, things can get quite slow quite quickly, like the more you use it, and it seems like you, in your setup, it's woven into like the core of your deployment for your application and your functions and your web pages. I'm curious as to what effect it's had on your team and whether you've had to spend a lot of time thinking about this or improving that.
Yeah.
Second, maybe answer that one first.
Yeah, I'll forget otherwise. Yes, it's a really good point. We quite deliberately make use of lots of small stacks. So that is a big kind of challenge you can run into with Terraform is you get large stacks that do lots of stuff and they become slow. And even with all this clever stuff that Terraform does around checking what it needs to update and everything else. So one thing is, because we can wire it together sort of nicely using TypeScript and JavaScript, we can manage the complexity, which might be harder to manage if you were using sort of native Terraform and calling it with Bash, of having lots and lots of stacks that do relatively small amounts. So in Terraform, a stack is like the thing you deploy as a stack. So when I did the deploy there, it actually deployed about 5 stacks rather than one big stack. And then we can manage where those get run. So we kind of think of them as like micro stacks, like microservices, where they have a small scope. And CDKTF lets you take the outputs of one stack and use them as inputs to other stacks in a way that's very straightforward. So you can wire up, and then when you run the CDKTF kind of binary run executor. It executes those stacks, but makes sure that it can take the output from one and pass it as the input to the other. But it's not building this huge dependency graph in Go and doing all of it. It's actually sort of coming out and just saying, I just take these two strings and pass them over to this other one.
Produce an abstraction, and then it complicates the Terraform world a bit. And if so, like, is
Yeah.
that a problem you'd like to work around? Or?
Yeah, so I think it's a really good question about Terraform. Probably for a lot of people who aren't familiar with Terraform, it may not be clear what's going on, but if I show this stack, for example, this is a problem that we run into. So when I make my Firebase project, actually a better example would be my storage object. Okay, so this storage bucket object has a name here called build. This is where we send up our zip file to Cloud Functions. That's the code that's going to be executed. This sort of string that's just loitering here, looking reasonably innocent, ends up as the name in Terraform. If I change the name of this, when I redeploy, Terraform thinks that what I've done is asked it to delete the previous entity and make a new one that's otherwise exactly the same but has a new name. If there are then dependencies on that object, all of those dependencies will get sort of deleted and rebuilt or updated and various things. And it's very easy to come into the TypeScript and start refactoring and being like, oh, I see we've got this called in a couple of places, right? I'm going to do a new function in here where it's like create Firebase, and I'm going to move that into a light. That was fun. Thanks, Copilot. So I move this into a function that's called kind of create Firebase, and in that function where I've like wrapped together some nice things, I've changed this to like the build, or it's like now a parameter to get passed in. A nice thing about this being in TypeScript is that you can do that, so we can kind of construct our own calls in TypeScript that bundle together a few different Terraform components that work together. For example, this thing of saying like a cloud function has to have some source code and a identity that it executes as, and that needs a bucket object things. We actually have that bundled into a single class, and we can just instantiate one of those and pass a few parameters. But when we do those kind of refactors, we cause this exact thing where the Terraform state suddenly is like, whoa, I have no idea what you did there. I'm going to start deleting everything and rebuilding it. And that can be slow. It can also sometimes be something that needs manual fixing, because the cloud then starts kicking in and being like, you can't delete those things like in that order. That's not okay. So we do have to be careful about refactoring, and we've become fairly disciplined about trying to get these things kind of right first time. So you do have to be aware of what part of the code you're working on, right? The front end of the Remix app can be sort of iterated on very rapidly, and if you make a mistake, it's not a huge deal. The Terraform gets executed and written into Terraform state that is long-lived, and if your Terraform state gets too mismatched with your Terraform program, then yeah, that can be a lot of work to unpick.
Right. Thank you very much, Andy. That was pretty much all I've had time for today in terms of sessions. Alistair, closing words?
Yeah.
What? So what? With YouTube or no YouTube? Okay. See, I was gonna thank Scott, but just kidding. All right. You wanna do the nice stuff first, or should we do the organizing stuff first?
Organizing stuff.
Organizing stuff. Okay. All right. So this was pretty much the sessions we've had for today, but community means talking, grabbing a beer together, and that kind of thing. So what we did is we booked a large table at Brewdog at 8:30. So we'll be here for like another 20 minutes. Then whoever wants to join us, we're gonna go there. If you could all grab your rubbish and throw that away in the bins in the kitchen, that would be amazing. Otherwise, I'm gonna have to do that, and I only have 2 hands. Yeah, and that's pretty much all organizing things.
Yep.
Perfect. Amazing thanks to everybody for being here. Like, it's been great. Our first community event we hosted ourselves. Yeah, it's been awesome. Thanks everybody for coming. Thanks to all the speakers. Thanks to all the sponsors as I started in my first session. And Alistair?
Sure. Okay. Yeah, thank you so much for coming. This has just been like an absolute huge success for me. 4 months ago when I said to Simon, whenever it was, the next conference, I said, maybe we'll do this. And he was like, yeah, I'm gonna hold you accountable. This is gonna happen. And he was messaging me on Twitter and saying, yo, you gotta start working. You gotta do this. So again, round of applause for Simon once again. He's just absolute legend. And a massive, massive thank you to Cloudflare for letting us use the venue, which has just been absolutely splendid. Such a convenient location and very on topic for us as developers as well. And also, we have Vercel sponsoring us. So some lucky few of you will get an email sent a bit later with some invite to some Vercel swag from the next conference. So thank you to Vercel for sponsoring that, which is pretty cool. Tom just got pretty excited at the front. Hopefully you can get an email. And yeah, round of applause to you all. Thank you so much for coming. This has been great.
See you all in the kitchen. And grab your stuff, please. Thank you.